Hello. Hello guys, how's it going? I'm just gonna check that my audio is good and that the video is good. Check that my audio is good and okay, that's good. Oh, perfect. So basically now we're gonna continue with our stream from today. Before I was on the stream number 39, that's gonna be the 40. And this is gonna be data science and algorithm review 2. And in this one we were doing tries, which is a data structure that is basically a tree, but each node is a character of a word, so it's used for search. It's called also prefix tree. We're checking that we can use this to make like word search, and we can do it. We just did it in JavaScript, and now we're gonna check it in Python. And well, we have here how is it done in Python. We have here, I mean, the basic try node. We have the init. There's no data in here. This is the base. With the children, we define the root is a try node. And then for each word, the current is equals to the root. For C in the word, in each word we initialize the current as a root, and then we see if C is not in the children, then we assign to the children list, children dictionary, sorry, try not. And then we pass the children to C to the current one, and then we'll be in the other node already. All right, and then in here we have something similar, but in this case, oh guys, it's so hot here. In this case, we will just append the suggestions that we sort based on lexical, and then we pop the from the array the last one. Yeah, more or less I understand this. And now let's go to the implementation. In this case, now we're gonna do the implementation in Python 3. Okay, so for this we will need to do in the init. I will need to make the how wait, I'm gonna open this in a new tab. and they need, we pass the self, so in this case we do self that children is equal to this, and then when we do string, it returns none. Then we do for character in word, we do if the character is children, assume, let's see the syntax. Is C not in self children, then what we do is self dot children. So we create a new try. We will try note there. Try note. But first here I need to do core. Or just like try. If current the children it's equal to children but C. And then kernel will be so it starts with node, I think. There's no commas here. This will be worth. because in the last and on the word D, and then it's gonna, let's see what it's gonna check on all the children, and it's gonna check if it's the next word. Okay, so then yes. Well, let's check this in Python in the, yeah, we're here in the chats. Oh fuck, let's use Gemini. But okay. Okay, apparently like here, we don't need to, I'm sorry, here. We don't need to save the val. We can just create something like is and this will be false. And this will be true. So then yeah, okay, so on the search, I don't know why I feel like the Python code is like shorter. Anyway, like on the search, I assume that it will be the same as here for seeing word. So I will do the current, it's equals to self. Return false. Else current is equal to C. And then when I finish, return cur that is end. So when I pass everything, yeah, I just verify that it's the end. So let's check this. And so far, false should be false. I was confusing with JavaScript. Run with the semicolon. Yeah, and I guess that here in the we should do something like this, but always just return true. Foreseen prefix. We're good, guys. We're good. Okay, so this was just the implementation on Python of the thing that we already did in JavaScript. Just to review, I'm gonna check like what are main differences between Python and Python 3 and Python. Meanwhile, we approve this. Let's go to bit manipulation. Bit manipulation is a, okay, 1 second. Come on, mate, I don't have the whole day here. Algorithms in clever ways. Bit manipulation involves looking at data in a variant form and manipulating the bits in this form. The most important operations you need to know are OR. If a bit is 1, and the end result will be 1, otherwise the result is 0. And if all bits are 1, the result will be 1, otherwise the result is 0. SOR. If the number of 1 bits is odd, and the result will be 1. So it will be either if one or the other. If both of them are 1, that will be 0. Left and right shifts. Shifts move all bits over one place in this respective direction. If the first bit is flipped, a right shift will delete it. So it corresponds to multiply or divide a number by 2. Yeah. I mean, if it's like bit, yeah. So okay, let's see. X or 1 will be 15. X and 9 will be 1, 0 is 12. This XOR will be 0, 1 is 3. Mm-hmm. Mm-hmm. I think number. Okay. And when people say Python today, they almost always mean Python 3. Historically, Python referred to Python 2. So, mm, okay, so Python 3 has type annotations already. In Python 2, that will be like a 7 over 2 will be 3, but in Python 3, to make 7 over 2 is 3.5 float division, but if I want explicit integer division, it will be double slash. Okay, so now let's work on Python 3, I assume, mostly. I'm just gonna check now that this resets at 7:30, so I have 15 minutes to keep studying this. And then I'll just take a shower because I need to what the fuck? Who is Nadeska Widowski? Who's Nadeska Widowski? Ah, it's a model in Peruvian. Okay. Uh, so okay, I don't know where the fuck I'm in YouTube now. Yeah, sure. So we have the bit operations right now here. Sometimes we want to focus on specific bits rather than every bit in a number. To do this, we can use something called bit mask, also just called mask. A mask with one bit flipped can be used to check individual bits of other numbers. For example, let's say the word concerned only about the second bit, 0 indexed from the right. Only about the second bit, 0 index from the right. So that the bit that represents the decimal number 4. 1, 3, 4, yeah. Okay. Mm. Okay, we can take an integer mask 1, left shift it twice, so it's in the second position 100, which will be a number 4. Now any operations between x mask will be applied on the second bit. If we want to see if the second bit x is flipped, we can do mask and x, because all bits in mask are 0. I don't know. Other than the second bit, this will be 0. Okay, if we want to see if the second bit of x is flipped, we can do, I really need to figure out how to use this, because so far I don't like this. We want to see if the second bit of x is flipped. Mask 1, let's shift it twice. Now any operations between x and mask. Will be only applied to this on the second bit. Okay, that I got it. What you want to see if the second bit of x is flipped? Because all the bits in mask are 0 other than the second bit, this result will be 0 if and only if the second bit in x is not flipped. This amplifies the result of mask. Wait, reductor. So okay, XOR flips it, so that means that if it's 0 and it's 1, it's gonna be 1, but if it's 1 and 1, it's gonna be 0. Yes, that's correct, because all bits in mask are 0. Other than the second bit, the XOR operation will not change any other bits. Yes. Yeah, okay, if you do XOR with 0, nothing changes. If you do this, then X flipped. Okay. Okay. So if I do soar with the mask, I will just flip. Um, I will just flip the index that I with the one. Yeah, let's see here. Okay, I think I got it.
Here we have the number 18, which can be
Oh, there's something here, finally.
represented in binary as 10010. So let's take a look at bit manipulation. The first idea is a mask. And let's say we have a mask which is just an integer and it's equal to 1. In binary, this is 00001. And the idea behind a mask is that if you perform left shifts on it, let's say we left shifted it once, this will move the bit over by one position. And no matter how many times you left shift the mask, let's say we left shifted it 3 times instead, you will never have more than a single bit set. So you can see we have a bit set in the third position, but every other bit is equal to 0. And when I say position, what I mean is, imagine from the right, you have the 0th position, and then you just count up. So right now, by left shifting 3 times, we have a bit in the third position.
Yeah.
And we can use this idea to answer questions about the original number, 18. Let's say somebody asked, is the third bit in 18 set? Well, we can see it's not, but to verify it with an algorithm, we can left shift the number 1 3 times to isolate a bit in the third position. And then we can perform an AND on the numbers. So with AND, it looks at each position, and at each position, it checks both bits, and it will set it to 1 only if both bits are set. So because with a mask, every single position is 0 other than the position you're focused on, these will all automatically be 0, and then this will depend on 18. And because the bit in 18 is not set, it will also be 0, and your result will be 0. However, if we change the question, is the 4th bit set, then what we could do is we could left shift mask an extra time, and now we'll have a mask which only has the 4th bit set. And now when we perform this AND, all the other positions will be 0, but now that both bits are 1, the bit will be set to 1 as well, and this number will be 16. Now, it doesn't actually matter what this number is. The only thing that matters is that it's not equal to 0, and this tells us that the 4th bit in 18 is set. We can also use masks to flip bits. So remember with XOR, if you perform an XOR with 0, nothing happens. So if we XOR these two numbers together, then nothing would happen to any of these positions. The bit will stay the same. However, for the 1 bit that we do have set, it will change that bit. So here you'll end up with 0. And this gives you a new number, which is 2. And that's what happens when you flip the 4th bit in 18. Now, let's say we wanted the 3rd bit instead. So we only left shift 3 times. So our mask looks like this instead. Now, if we perform an XOR, again, at all the 0 positions, the number won't change in 18. So we'll have 1, 0, 1, 0. But now, since the bit in 0 isn't flipped, it becomes flipped. And this gives us a new number. So to summarize, we can left shift the number 1 to create a mask which focuses on a certain bit. And then we can use AND to check if a bit is flipped, and we can use XOR to flip bits ourselves.
Okay. Okay, I don't know where this is useful for, but let's see. Okay, now it says single number given a non-empty array of integers nums. Every element appears twice except for one. Every element appears twice except for one. Find that single one. It is giving me already the vibe that it can be used for similarities and, finding like patterns. Given a non-empty array of integers nums, every element appears twice except for one. Hash map to count the frequency of each element. And then, yeah, this will be O(n), which is time and space, where n is the length of the input array. To improve the space complexity, you could sort numbers. Each element doesn't appear twice. Depending on your language sorting, this could be lower space complexity, O(n) or log n. Recall the stock or sort. If the number 1 bit is odd, then the result will be 1. If one of them it's 1, that's will be 1. Otherwise the result is 0. The number that we're looking is the only number that appears an odd number of times. Because if it's 1 1, then it will gonna be 0. Okay, so if it's 1 1 1, it's gonna be 0 1, then that's gonna be 1. If it was 4 times 1, it's gonna be 0 1 0. Okay, so technically speaking, XOR with every element in the array, because even other numbers appear twice. Oh, there's no here. Mm, nope, I understand. Mm, but this is doing. If the numbers are equal, then we're gonna get 0. And then we get 0. Oh, but are these sorted? In a space of 1, because we don't need to save nothing. So to give us ON. No. I will ask help to Gemini to a deeper explanation. Any number stored with itself returns in 0. Every bit that much as. Okay. Any number stored with 0 stays unchanged. Order does not matter. Okay, so I can just XOR everything, and the numbers that are duplicated are gonna give me 0, and the numbers that are not duplicated are gonna prevail. And because of the fact that there is only one non-duplicate, then that is just gonna be prevailed. Okay, because order doesn't matter. Okay, I understand that the order doesn't matter, but can you please explain why does order does not matter of XOR of multiple numbers? So in this Python, you see that I just like, and now this operation is like the same as doing mask is equal to mask x num, and then I read, and then I mask each number until I get the mask, and the mask is actually the number. Okay, because I don't need to create I just create a new variable here. Swapping A and B produces exactly the same result every time. Okay. Associative. Okay. That's I didn't know that there's associative property. That's nice. Yeah. Yeah. I mean, if at the end of the day, the yeah, it just makes sense, because if I'm doing bit, if I put it in every in the whatever the order it is, I will see that the if it's like odd, it's gonna be 1, and if it's even, it's gonna be 0, and all of the zeros we can just keep 0. So we're just gonna at the end up with the number that has the odd numbers of ones. Okay, it just makes sense now. Okay, that's good. Okay. Bit mask are hashables indicators of visited. Yeah. Backtracking on DP problems, dynamic programming problems. We saw problems that involve using elements from array at most once. When we have a problem like this, it is useful to have an indicator of which elements we already used. We could use an array, where array is a boolean indicating the ith element has been used. The problem is we can't hash arrays, so using a viable solution in Dynamap. We have run this is an indicator of which elements we have already used. The problem is we can hash arrays. Most states we could use tuples which can be hashed. Oh, I'm saying Rapify, sorry. We could use two tuples which can be hashed. Number of queens to okay, I'm just making some arrangements in here. How long we're streaming already? It's 12 minutes, impossible, man. 55 minutes. This shit is a lot. It's a lot, guys. Mm, in our previous solution, we used a set to store columns from 0 to n. I don't remember that problem from from dynamic programming. Maybe I actually didn't did it. I don't remember this. Alright, let's open it. Okay, I'm gonna ask this to Gemini. Uh, I think I'm gonna tell. I think we need to first explain how did we solve this with TP. Backtracking. Sorry. And queen subpronouns do not overlap. Every word configuration you're reaching are. Uh, oh, fuck it. Okay, I'm a bit tired. I think I'm gonna check that later in peace or tomorrow. Because I understood the bit mask, but I will need to come back a bit to the backtracking to just check about this and queens too first on the backtracking and then to check it again but with the beats, right? But thank you very much. It's a pleasure.